This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning, everyone. So I just want to remind you that midterm test will be coming soon. We think at the moment it will be in 2 weeks during this lecture time. So it will be online. You will get more instructions soon through LMS. So you will have to just do it pretty much during this lecture time. You don't have to turn up for lecture when the midterm happens, but just make sure that you have all the compatible, browsers and software, and instructions will be sent to you, and you have to have a reliable Wi-Fi, right? So a reliable link, so that you don't have any problems. All right, so there will be more instructions coming your way. Now, why I mentioned this, you still have 2 weeks to prepare for this. I hope that you are already studying very hard. So all the material from first 18 lectures, or in other words, whatever comes in the first 6 weeks, will be accessible. I know that we are 1 lecture behind because I was sick, but that lecture will be covered still before the test, right? So I urge you to study hard already, because it will be a good feedback to you on how you are going with the material, right? So midterm test is feedback to you on your progress on this subject. All right, so today's lecture is very technical. It's packed with calculations and, basically we will learn in today's lecture how to sketch root locus, general root locus, and we will work through one example step by step. So I will be introducing the general rules for sketching the root locus, and then we will be applying these general rules to one example. So after this lecture, you should be able to sketch any root locus, and please practice this, because this is the material that will be assessed. I mean, pretty much everything in first 6 weeks of the subject will be accessible, but root locus is definitely one of the important topics, right? So here is the outline. It's rather packed, and I will keep going. Please slow me down if I'm going too fast. I'll try to be as clear as possible, but we have a lot of material to cover, so I will keep moving quickly. So we will first recap briefly the last lecture, just to remind you what locus is, and phase and gain conditions, because we will often use phase and gain condition in today's lecture to sketch root locus. And then we will go through those basically main steps of sketching root locus. So we will talk about branches, poles, and zeros, asymptotes, parts of real line on the root locus, intersections of the imaginary axis, multiple roots, angles of departure, arrival, and then we will wrap up. By the way, in yesterday's lecture, I just I defined each of these, and I promised that in today's lecture we will learn how to plot these things. So you will already have seen all of these last lecture, and today we want to just present rules, formulas on how to actually plot these for an arbitrary system, and then we will wrap up with conclusions. So to remind you, we will start from a formula that looks like this: 1 plus k times f of s, where f of s is a rational function. It has a numerator denominator. We will assume that it can be written in this way. So beta k's are zeros of this transfer function f, and alpha k's are poles of f. I remind you that f doesn't have to be open loop Planck transfer function. You simply can, using algebra block diagram, arrive at an equation like this for a very general class of systems. So we can consider robustness to Planck parameters. We can consider controllers that are not just proportional gain controllers. We can cover lots of cases. But the starting point is this. So you've already done your algebra block diagrams. You've got the characteristic equation, right? So this is the denominator of the transfer function for the closed loop system, for the overall system. And you have to rewrite it in this way. That's the starting point in today's lecture. Okay? So we will assume that k varies from 0 to infinity. In other words, we will be plotting all the rules that I will be giving you for the so-called positive root locus. So gain k is positive. All right. So just to remind you that if a point is on the root locus, if point S0 is on the root locus, it has to satisfy that equation. So points that are on the root locus satisfy that equation. Points that are not on the root locus do not satisfy this equation, right? So, but because we know that this holds for all points on the root locus, that's the same to say that kfs0 is equal to -1 for every point S0 on the root locus, right? So, and from here we can extract, yesterday we showed that magnitude and phase conditions hold. So basically, magnitude of k times f of S0 is equal to 1 for every point on the root locus. And similarly, phase of k times f of S0 is equal to this. So it's pi plus minus pi plus minus 3 pi, etc., right? So why is this the case? Well, when we take magnitude on both sides, left hand and right hand sides, we get this magnitude condition. And when we look at the phases, phase of this has to be the same as phase of that. Well, phase of that is exactly this, right? So and since k is positive, phase of k is 0, right? So actually, phase of f should be equal to plus minus pi, etc. Right? So phase of k is 0, and phase of k times f is phase of k plus phase of f. So then we can say that phase of f is equal to the right-hand side here. So these are the phase and gain conditions that we will be using in sketching root locus over and over again, right? So different parts will be sketched using these rules. So now we want to go back to the main features. In yesterday's lecture, I introduced these things and defined them on an example. I defined what are the branches. I defined open loop zeros and poles. And also parts of real line that belong to root locus, asymptotes, breakaway points, or that these are the points where branches intersect, intersection with the imaginary axis, and angles of departure or arrival. So we introduced these in yesterday's lecture. So we will now go through each of these and show how to plot them in general. If I give you general f of s, general transfer function f of s, then you will learn how to sketch each of these, and then in the end sketch the full root locus. Right? So the idea here is, look, all of these are just giving you certain features of root locus. They're not giving you the full story. But once you plot all of these, you will have enough information to just connect the points together and sketch the root locus using this information. Right? So that's very useful, and as I said, it's not just because, you know, in exam we don't have computers. Intuition that you gain through sketching root locus is really invaluable for you as a control designer. So if you look at the system, if you think root locus way, you can quickly see how proportional or integral controller would affect your system. Very quickly, for many systems. Right. So that's why it's so important. Right, so we now want to go through each of these and show how to plot these things in general for a general transfer function. And we will be going through an example step by step. So the idea is to illustrate each of these on an example as we go. So, well, the root locus will have L branches. And L would be the maximum between numbers of poles or zeros. Now, for the transfer function f, when I talk about poles and zeros, I always talk about f transfer function. So this guy, right? So beta k's and alpha k's are poles and zeros of this transfer function f. This transfer function f may not be planned or controlled transfer function, but it's obtained from them using the block diagram. But I talk about poles and zeros of this guy whenever I talk about root locus sketching. So note that this guy may have, well, n poles and m zeros. And note also that since f doesn't now come from a system, it's just a mathematical construct, this may not be a causal system. So we may have more zeros than poles. Might have more zeros than poles in this case. So, but what is the number of branches? Well, the number of branches is the maximum between n and n. So it's a maximum between number of zeros and number of poles. Right? So, if that is causal, then L is obviously equal to the number of poles, because the number of poles will be larger than the number of zeros. But if it's not causal, then it will be the number of zeros. And as I said, it may not correspond to a model of a physical system, so we can mathematically deal with something that's not causal, just for mathematical purposes. So we will consider this example. So I'm introducing now an example that we will revisit through each step. As I introduce one of these features of the locus and I show you how to calculate it or plot it, we will revisit this example over and over again. So here is the example. So note that I picked on purpose an example where controller is not just a proportional controller. So what I do here is, well, I do have that controller depends on some constant k, and I want to plot root locus with respect to this k. So what I need to do first is I need to find what's the transfer function of this closed loop system. So I use algebra of block diagrams and I find the transfer function of this full system. And then whatever is in the denominator would look like this. So what's in the denominator of that closed loop transfer function would look like this. So, and that's the starting point for me. I divide, so I call this d of s, I call this m of s, I divide everything by v of s, and then I can rewrite this equation, this polynomial here as 1 plus k times m over d equals 0. But now m and d come from controller and plant, but they come in a strange way. I mean, using the algebra block diagrams, we calculate them, right? But they're not just plant transfer function or control transfer function. So this is the f function, m of s over d of s is the transfer function that we need to deal with for this example. So obviously the first thing that we need to check is what are the poles and zeros of this transfer function to see how many branches we have, right? How many zeros we have? Well, m of s is this, right? So what's a zero? Minus 10. And what are the poles? Well, the poles are a bit tricky. I can see that there is one at 0, but then we don't know the other two, right? So, but we can easily find, let's use MATLAB. MATLAB can help us to rewrite the transfer function this way. The transfer function f can be rewritten in this way. So just using these commands in MATLAB, we can arrive at this. So this is your transfer function that you are dealing with in this example. So poles are then at 0, minus 2.91, minus 8.5, right? So how many branches do we have in this case? 3. Because there are 3 poles, 1, 0, maximum between 3 and 1, there are 3 branches. All right, so that's it. So look, this looks very simple, right? Let's look at the open loop pole zeros. Well, why are these important? Well, we'll analyze that now. So note that if I look at this transfer function, formula, 1 plus k times f of s is rational. I can rewrite this as d plus km over d, right? I can rewrite this. This here is equal to that. So when is this 0 for small k? Well, when d is equal to 0. So if k is close to 0, then k times m is negligible. So actually the roots of this thing here are the same as the roots of d of s equal to 0. And what is this d of s equal to 0? Well, that gives me poles of f, right? Because f is m over d. So if I cross multiply everything by d, I get d plus km, everything is divided by d, right? And then when k is small, then d of s equal to 0 is, giving me the points on the root locus. So in other words, for k gain, k small, we will have that the zeros of characteristic polynomial for the closed loop are roughly equal to the poles of the open loop transfer function. What I mean by open loop transfer function is this f. That's what I mean by that. That's the terminology I use. So, in other words, we can say that branches, all branches of root locus emanate from poles, because k would be growing from 0 to infinity. So as k grows, it starts for k equals 0. So the branches will emanate from poles. That's why it's important to always to input these poles locations of f into the complex plane. It will help you sketch the root locus for an arbitrary system. How about zeros? Well, why zeros are important? You know what, if I rewrite everything now in this way, so I took k out, and then I rewrote everything as 1 over k d of s plus m of s. Now, since k is positive, if k is very large, then now d, this 1 over k d would be small. So then we have that for large k, m of s equal to 0 would be where some branches would end up for large k. And what does this equation give you, m of s equal to 0? Well, they are all zeros of the open loop transfer function, or f of s. Right? So they are zeros of f of s. So, by the way, in the example we saw, we had 3 poles and 1 0. We already said that there are 3 branches, maximum between poles and zeros, numbers of poles and zeros. So there are more poles, so there will be 3 branches. We said also that each branch would emanate from each open loop pole. From each cross, there will be 1 branch coming out. And for large k, branches will end up in these circles. But note, we have 1 circle and we have 3 crosses. So what will happen with 2 branches? We know that 1 branch would end up in a circle. For large k, 1 branch would converge to the circle. But what would happen with 2 other branches? What do you think? Yeah. So there will be some branches that go up to infinity. And this is actually where there comes a term. We talk about zeros at infinity. So we sort of say, okay, there are some zeros at infinity. Right? There are some zeros that are finite zeros, and there are some zeros at infinity, and these asymptotes will converge to those zeros. So how many asymptotes should we have in this case? 2. And you will see, we will learn how to plot these, right? We will learn how to plot these asymptotes as well. All right. So crosses are the poles of f of s, and circles are zeros of f of s. In the equation 1 plus k f of s. That's what it is. Always you need to insert these things in the complex plane when you are plotting a root locus, right? It's an essential feature of any root locus. Right? Now we need to determine segments of the real line that belong to root locus. Now you may ask yourself, well, why do I bother about real line? Why don't I bother about imaginary line or imaginary axis or some other axis in the complex plane? Well, the reason is because plotting this is extremely easy, and determining whether an arbitrary point, let's say our imaginary axis, belongs to root locus is much harder. So this is very easy. So since it's so easy, let's do it, right? So we will just have extra information when we are sketching our root locus. Why is it so easy? Well, I remind you that phase condition has to hold for every point on the root locus. So if I pick S0, then this phase condition should hold. Since k is positive, you know, phase of k doesn't play a role. We can just talk about phase of f, right? And moreover, you know that all poles and zeros will be either complex conjugate or they will be real. Right? There's no other possibility. But then, if I now take the test point S0 to travel on the real axis, and I'm asking, is this point on real axis part of root locus? Is this point part of root locus? Is this point part of root locus? Etc. If I just go through the whole real line and test using the phase condition, then the contribution from any complex conjugate poles or zeros would cancel, right? Sorry. So it would cancel. So we do not have to worry at all about complex conjugate poles and zeros. Because in the end, they will always appear in pair. So if this was the phase of S minus gamma, then the complex conjugate phase will be just the negative of that. So that's why, you know, this would be very easy to actually plot. So then, what is the, if I consider some, let's say, pole or zero on the real axis, and then, you know, the test point S is here, well, what is the phase of S minus gamma? Well, in this case, what is the line that connects gamma with S? Well, that's this guy. And what is the angle between that guy, that line, and the positive real axis? It's 0. So actually, when we are to the right of a pole or zero, then the contribution of that pole or zero is 0. The phase is 0, right? And when we are to the right of such a pole or zero, gamma, then the contribution would be pi. So it's actually very, very easy to test whether a point on real axis is part of root locus or not. Why? Because I only need to look at real poles and zeros of F and then apply this simple test. If I'm to the right, then the contribution of that pole or zero is 0, and if I'm to the left, then the contribution is pi. So I can quickly determine which parts of real axis belong to root locus. Let's look at that in the example. So when I consider, let's say, this test point, well, what is the contribution of all poles and zeros? What are the phases with respect to this point? They are all 0. They are all 0. All the contributions for all these poles and zeros are 0. Right? How about this if I say test point is here? Right? Well, contribution from this guy will be pi, because when I connect that guy to this point, I have pi, right? And the contribution of all of these guys are 0. So now I have that for any point on this part of real line, I have that my phase condition holds. So this part of real line does satisfy the phase condition. All of the points on this part of real line. Are there any questions? Am I going fast? How about test points here? Well, contribution for this pole and this pole are pi each. And contribution of these two guys are 0 each. Now you will have something that's like minus 2 pi or 2 pi. That's not satisfying phase condition. So none of the points on this part of real line belong to root locus. How about this point here, any point here? Well, contributions of all of these guys are pi. So I will have minus 3 pi, right? Contribution from the 3 poles, contribution from 0 is 0. So obviously, these points here, again, satisfy phase condition. How about here? Well, contributions of all zeros and poles are pi each. But remember that zeros and poles come in with negative signs. So 1 0 and 1 pole would cancel, and I would have just contribution of 2 poles. So it's again minus 2 pi. Again, doesn't satisfy phase condition. So none of the points on this part of real line satisfy the phase condition. So, what is the general rule? How can you quickly figure out, you know, which part of real line belongs to root locus? Well, look, if you are to the left of an odd number of zeros plus poles, you are good. If you are to the left of an even number of zeros plus poles, then you are not okay. So that's an easy, very, very easy. By the way, here you have to take into account multiplicities. If there was a situation where you had 2 poles at the origin, then this part of real axis would not belong to the root locus. You have to take multiplicity into account, right? But the good thing is, I do not have to worry at all about complex conjugate poles and zeros. because their contribution cancels. So look, now you can see that this is like a crossword puzzle. It's sort of interesting because we are now learning more and more about our root locus for this example. So now we know that these parts of a real line would exactly be on the root locus, right? So we plotted part of the root locus. We need to also, well, we need to have more information to actually sketch the full thing, but we are learning about it. Every step gives you more information. Right? So now we want to talk about asymptotes. By the way, I mean, what we already, let's just think about this branch. We already learned that for small k, the root locus will be close to this cross, because the root locus, solutions for the closed loop sort of equation, like poles of the closed loop, would be close to the open loop poles. In other words, they would be close to these crosses. As k is increased, this branch of root locus would move from this cross to this circle. So for very, very large k, we will be close to minus 10. So we know pretty much everything we need to know about this branch. So in this particular example, that branch, there's nothing else to add. That's it. We know everything. I mean, it's a special case, right? But in this case, this branch is done. We will not change anything about this branch. Now, why we haven't finished this part? Well, because of the asymptotes. Because these two guys will somehow have to converge to infinity, and we don't know where and how. Whether they would go this way to infinity, that way to infinity, that way to infinity, I mean, we don't know. We need to plot the asymptotes. We also need to know, in going to infinity, whether these guys, whether these two branches, so by the way, branches emanate from crosses. So they start here for small k, and then they would move somewhere here. Now, at some point, we would probably have, definitely have, like a branching point, because these two branches would meet as we increase k. We will have, for some k, multiple poles at the same point, and then it will branch out somewhere. Now, when it branches out, these things will go to infinity as k goes to infinity, but we want to know also whether these branches would cross imaginary axis in doing so. Why? Because we want to know whether we can destabilize the system by increasing the gain. We want to understand whether the system is stable for all positive k, or whether there are some k's for which the system is unstable. So we need to have much more information to learn about these remaining branches, right? So asymptotes. First I will present you formulas for asymptotes, and then we will talk about how where they come from. I won't go to the proof. I mean, Ogata has a nice proof. I will present you equations. I encourage you always to go through these equations, but I want you to know how to use these equations, right? What they mean. So, how will we plot asymptotes? We will plot asymptotes by giving two pieces of information. One piece of information is where asymptotes intersect the real axis, point at which they intersect the real axis. And another piece of information is the angles of asymptotes that they make with respect to the real axis, positive real axis, right? So with these two pieces of information, I can plot any asymptote. Right? So it turns out that you can quickly write the point of intersection of all asymptotes. It turns out that all asymptotes intersect at a single point. All asymptotes intersect at a single point of real axis. And that point is given by this formula. So it's a sum of all poles minus sum of all zeros divided by n minus m. Now n is the number of poles and m is the number of zeros. Now you may ask yourself, where does this formula come from? I will explain in a moment where it comes from. And then the angles are given here. So the angles, there will be n minus m asymptotes. You know, in this example, we said there are 3 poles, so there are, and 1 0. There are 3 branches. One branch would end up in a 0, and then we are left with 2 branches where they would end up, well, at infinity. So the number of asymptotes is really the difference between n and m. I'm here assuming that there are more poles than zeros. I'm here assuming there are more poles than zeros. So I'm assuming f is causal. So what is the formula? Well, the formula is given here. Well, you know, you have to change k from 1 to n minus n, where n minus n is difference between number of poles and number of zeros, and you have to divide by n minus n. Now, what does this mean, right? Well, we will show this. It's very, very simple to explain this. By the way, this situation, n minus n, you have it in Michael Cantoni's notes, so you can look it up. You know, I would typically give you, causal f's, just for simplicity. But you can have more general situation. There are formulas for that in the lecture notes. Now, how do we, so let's first explain where sigma comes from. I want to explain how you arrive at this. But you know, the detailed proof is given in Ogata's book. And I will just explain here. So I can, I start by considering f of s, where f of s can be written as product of s minus zeros and product s minus poles, right? So I can rewrite everything in this way. So what I did, I divided everything by the numerator, right? And then I rewrote the denominator in this way. So what I have here, because I'm assuming that n is greater than m, then I have something like this. Now I have a polynomial is in S, and then I have a rational function in S. Now as S goes to infinity, by the way, asymptotes are really the situations where S becomes very large. So I have to consider the case when S is very large. So note that this guy here, because here I have s to the power m minus 1, here I have s to the power m. So when s is large, all of this will go to 0. And then I'm left with this polynomial, but because s is very large, I'm considering just very large s's, then only the first two terms will dominate the overall behavior. So then the other terms will be negligible because I'm taking powers of s, and s is large. So I'm just going to concentrate on the two highest order terms. Well, it turns out that you can rewrite this thing here as 1 over s minus sigma n to power n minus n. Why is that? Well, I leave you to look up the Laura's book. It's simple algebra. It's simple algebra. But from here, when you think about what is the coefficient a n minus 1 and coefficient b n minus 1, do you remember polynomials, right? If you rewrite polynomials, so you start from something like this. So polynomial is s minus alpha k product of all of these things. And then if you multiply these out, and then you look at the second highest coefficients, the coefficient that multiplies s to the power n minus 1, you will see that that coefficient is the sum of alpha k's. Right? So the second highest order coefficient in that polynomial would be the sum of alpha k's. And this is where these sums of alpha k's and beta k's come from. Right? Now this n minus n comes from the fact we are also trying to rewrite everything as 1 over s minus sigma n to power n minus n. Now sigma can be calculated like this. This is simple algebra. And then, for large s, roughly we will have that f of s would behave in this way. Sigma is given by this formula, and now the angles we will need to determine in the next step. Right? So the phase condition for 1 plus k over s, 1 over s to the power n minus n is given by this. Why is this? Well, I'm looking at phase of 1 over s0, n minus m of those, because there is n minus n power, and that's equal to the phase of minus 1, which is equal to that. So then I say, well, phase of s0 will be equal to this for k, ranging from 1 to n minus n. You can quickly check these formulas. Rather than sort of going into algebra of these formulas, I want to present just what this means for different cases when n minus m is 1, 2, 3, 4, etc. It's very easy. What you end up with, you're basically dividing a pizza, right, in equal parts. So basically, well, for n minus m is equal 1, there is one asymptote, and actually that's the real line. When n minus m is 2, there will be one vertical asymptote. We don't know where sigma is, but the angles will be really pi half and 3 pi half. Right? For n minus m equal to 3, you will divide pizza in equal parts in this way, and then when it's 4, in this way, etc. So you're always dividing 360 degrees into n minus m parts, equal parts. Now, where this sigma is, well, we gave you the formula before, so this is the formula. We have to plug in all the poles and zeros and the relative degree. By the way, n minus m is the relative degree for the transfer function f. So you plug it in this formula, you get to where all these asymptotes intersect the real axis. So now that we have a formula for sigma, and we know what these asymptotes would look like in general, well, in our example, what would happen? N minus m is what? In our example, 2. We have 3 poles, 1, 0. So 2. What's the situation we're talking about? This guy. So we know that there will be 2 asymptotes. By the way, there is a single line, but I said there are 2 asymptotes. So one asymptote is going down and one asymptote is going up, starting from real line. That's how I think about asymptotes. So each of the asymptotes will correspond to one of the branches of the root locus. One branch of root locus would converge to each asymptote as k goes to infinity. All right? So now the only thing that is left to do in our example is to calculate sigma. We know that we will end up with this situation, but we don't know whether asymptotes would be here, or here, or here, right? Where sigma would be. So we need to calculate that. So in our example, you basically, this is the sum of poles, 0 minus 8.5 minus 2.9, that's the sum of poles. Then minus sum of zeros, but 0 is minus 10. So minus 10 and minus in front of all zeros gives you plus 10, and we need to divide by n minus m, which is 2 in our case. The relative degree is 2. So that's the formula. We get minus 0.75. So we know already that we have 2 asymptotes, one going up, one going down, and we just found the intersection with the real axis, which is minus 0.75. So we are getting more and more information about our root locus for the example. All right, so now we want to give a formula for where branches intersect. So I said for each pole of the closed loop there corresponds one branch. Now there may be some situations where branches are sort of going towards each other and they might intersect. At points of intersection of branches, we will have that the closed loop has poles with multiplicity higher than 1, depending on how many branches intersect. If only 2 branches intersect, we will have pole with multiplicity 2. But you might have situation where many branches intersect. 2, 3, 4, 5. You know, we can have many branches intersecting at the same point. So we want to first present the formula, and then we will apply it to the example again. So first I want to remind you, or sort of present like a fact. If we have a polynomial with repeated 0, so then that polynomial can be rewritten as s minus alpha squared times some other polynomial. And that should be 0 because s will be a 0. So s equal alpha is a 0 of that polynomial, original polynomial, with multiplicity 2. Now, if I look at that, obviously s equal alpha is a solution of this equation equal to 0. But note, if I take a derivative of this, then the derivative is equal to this. So I have 2 times, so I take derivative of that times that, plus derivative, so times plus that times derivative of that. So this is basically just the derivative of a product of 2 functions. But note now that we have here s minus alpha and we have here s minus alpha squared. So note that s equal alpha is also a 0 for the derivative of f. So this is a way to pick out a condition that gives you multiple roots. So any alpha that solves fs equals 0 and the derivative of f with respect to s equal to 0 at the same time would be a root with multiplicity. So multiplicity higher than 2. Maybe this root is or even high multiplicity, but if you have just derivative and function being basically 0 at that point, the same point, then definitely there is multiplicity at least 2. So this is just an observation, but this observation would give us a formula for actually calculating points where branches of root locus meet, which correspond to multiple poles of the closed loop transfer function. You can actually, so Ogata does it differently. I will just present one formula. So if we consider this function f of s, which is basically the denominator of our closed loop transfer function equal to 0, well, k at which multiple roots occur, can be obtained by taking the derivative and calculating for k, and then substituting that k into the original equation. Right? Note that here we have function that depends on k, right? So I'm using this idea of the derivative, find the derivative, solve for k, and then plug that k in the original equation, right? So that will give you this equation, and that equation, solution of that equation will give you the multiple roots. Okay? So the idea is exactly the same as what I had here, right? We are just dealing with special structure of the formula that we have, right? So d and m are polynomials. So what you need to do is you need to find a new polynomial, which is d times derivative of m with respect to s minus derivative of d times m. And you have to set this to 0. Now that will give you, the points where you would, obviously these points need to be on the root locus. This equation might give you extra points that are not on the root locus. But points that are on the root locus and solve this equation are points where we have branches crossing. Okay? I will not look at this alternative approach. This is given in Ogata. You get the same formula. You get exactly the same formula. So we'll just keep, because we're running out of time. So I just want to now apply that equation that I gave you to our problem. So if you find this dk ds equated to 0, so basically the formula we gave, the formula that we are applying is pretty much this, right? So when you find solutions of this equation for that example, you would find that one of the solutions would be on the root locus. And this triangle here turns out to be that solution on the root locus. Note that this equation is third order, so there are two other solutions, but one solution is on the root locus, and that's the one where we have the branches are meeting. So note what this tells you now. So now we know more about root locus. We know that one branch would emanate from this pole. It will start moving towards this triangle, and another branch will start from this pole or blue pole and will start moving towards this triangle. When they meet for certain value of k, they will meet. There is a certain value of k where both branches will be at the triangle. And at that point, they will have to branch out. Now, we know that they will have to branch out, and eventually one branch would have to tend to the asymptote that goes up, and one branch would have to go to the asymptote that goes down. So we've learned much more about root locus by finding this triangle, because that would give us the point where branches sort of separate from real axis. Now note that depending on the example, this triangle may have been here or somewhere else. That depends on your problem. All right, so the question is, now, well, would these branches that meet here, would they actually do something like this? Cross, imaginary axis, and then converge to the asymptotes, right? Or would they stay all the time in the left half plane? So I still want to check whether these two branches will be crossing the imaginary axis or not. So how do we check that? Well, using Ralph Hurwitz criteria. So what we do is we calculate the Raud-Hurwitz array for the characteristic equation parameterized with k. And then we just check whether there are any changes of sign for the first column given, you know, k going from 0 to infinity. So let's just plot in this case. By the way, this is an example that I gave you earlier when we were dealing with Raud-Hurwitz. So this example you've already seen. This was calculated for you. So we just plug in, you know, all the elements in the Raud table. By the way, which polynomial do we need to consider? Well, I have to go back far. Which polynomial do we use for Raud-Hurwitz? Well, that polynomial here. That's the starting polynomial that was parameterized with k. And now I have that polynomial, and then I insert these coefficients of this polynomial into the Raud-Hurwitz array. Right? Calculate all the Raud-Hurwitz array, and then I see whether the signs in the first column will change or not as k varies from 0 to infinity. So this was done already in one of the previous lectures. We calculated Raud-Hurwitz array for this example, and this is what we got. And what we found is that the first column does depend on k, but k is positive. So now that if k is positive, then there will be no changes in sign in the first column. Since k is positive, everything will be positive. So we are good, right? So what does this tell us? We do not cross imaginary axis. We never end up touching the imaginary axis, nor do we end up in the right half plane. So those two branches that we are still trying to figure out what they are doing, right, will definitely stay forever in the left half plane. Okay? So, now, this is all you need for this example to sketch the root locus. Now, sketching, connecting things together takes a bit of practice. So you need to do a lot of examples to get the hang of it. But, you know, if you do maybe 10, 15 examples, you know, and by the way, you can go to MATLAB and just plot these things quickly so that you get a sense. Just give it different transfer functions, just see what MATLAB gives you to get intuition of how to connect things. But if you know, I will, by the way, just go straight because I'm running out of time. I'll just give you, I will go back to the larger angles. I just want to show you, with the information that we've already got, is basically, that's enough to actually sketch root locus. This point here is the triangle, right? The point where asymptotes intersect real axis is this point. We calculated all that. We calculated the asymptotes. You just needed to basically complete the root locus. We know that no branches end up in the right half plane. So actually, this is the root locus that MATLAB generates. Now, with the information that I gave you already, that we calculated, you can do this. So you know that when you meet the triangle, two branches will branch out, and they will have to follow the asymptotes. Well, this is what happens in this example. Yes?
You would always be symmetrical.
Yes. 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 Why is that? Yeah, you always have complex conjugate. So polynomials with real coefficients would either have real roots or complex conjugate roots. Yeah. By the way, there is a thing called symmetric root locus, which is then also symmetric with respect to imaginary axis. And that arises in advanced control when we do optimal control. So there is a thing called symmetric root locus, but that's symmetric then with respect to both real and imaginary axis. If we don't say that it's symmetric, then it's always symmetric with respect to real axis. Yep?
So if we cross the imaginary axis, would you cross the asymptote and come back?
That depends on the example. That's really, you have to sort of, it's like a crossword puzzle. You are finding out more and more features, and then you have to look at it and sort of connect the points. But that really depends on the example. You might have situations where root locus ends up, you know, in the right half plane, comes back, and it crosses again, comes back. You can cross the imaginary axis several times. Okay? All right. So we are running out of time. Now, I would like you, so for this example, we did not need around the departure angles because it was, trivial in this case. But please cover this. It's very simple, application of the phase condition. So if I want to basically see, I have a pole like this, and I want to determine whether the root locus goes in this direction, or that direction, or that direction, or that direction, I can calculate actually in which direction it goes by using the phase condition. I calculate, phases with respect to all the remaining poles and zeros, and I sort of say, okay, test point, is in the neighborhood of this guy, but close to this guy. So basically, phases of all the poles and zeros that are far away will not change much, right? But then I can calculate, this guy exactly by just plugging the formula for phase and calculate that one guy from all the others. Right? So it's very easy. All right, so this is before we wrap up, what do you think would be the root locus for this guy? I claim, it's trivial to plot. Why is it so? Why is it so? Why is it trivial to plot root locus for this guy? So, what are the poles and zeros of this transfer function? So we have 1, 0 at 1, right? 1, 0 at -2, pole at 0, pole at -3, and then pole at -10. There are no complex conjugate poles or zeros. All poles and zeros are real. All right, well, so let's determine the parts of real line that belong to root locus. Does this point belong to root locus? No, because the phase condition doesn't hold. How about this point? Yes. So this part, let me just use different. This part belongs to root locus. How about any point on this line? No, because phase condition doesn't hold. How about these points? Yes. How about these points? No. How about these points? Yes. How many asymptotes do we have? 1, because there are 2 zeros, 3 poles. So this thing here is the asymptote. So it just keeps going forever, right? That's the root locus for this system. That's it. There's nothing else to add. Each branch stays on the real axis. So basically, as we increase gain k, this branch goes from cross to 0. This branch goes from cross to 0, and this branch just goes to infinity, -infinity. So what can we say about this system? So tuning k, in this case, the gain, would never stabilize the system. You should be, guys, able, if I give you a transfer function, arbitrary transfer function, you should be able to quickly see, what's going on. It gives you a lot of intuition, and this is all about design. This is not analysis. I'm talking about whether you can pick a design parameter k to stabilize the system. And the answer in this case is no, because one branch is totally in the right half plane. Yeah? Okay. All right. So just what we did, we basically went through each step and learned how to plot features of root locus, arbitrary root locus. And once you calculate all these features for your example, you should be able to connect the points and sketch the root locus. It doesn't matter, if your branch goes this way or that way, just as long as you capture qualitatively, the features of root locus, you are good. And you need to do a few examples to learn how to do it. Okay? All right, so that's all I have for root locus. Are there any questions? All right, thank you very much. I'll see you this afternoon.
directly determine that this one is in the this one is allowable, right? How, according to the formula, it should be adding up all this.
Let's take it outside. I'll talk to you, but we need to go outside.